Hello, Sarah. This is Ed Leidenberger, your friendly Moodle Meister and physics tutor. So, the two problems that you had issues with are pretty standard kind of Newton's second law and then kinematics applications. So, for this first one, I drew a free body diagram. You've got the student moving a box of books via some rope that's attached, right? And they give you numbers, numerical values. I tend to like to work things out with the variables first. So I set up the free body diagram. You have a normal force in the what I'm going to call the positive y direction, the gravitational force mg in the negative y direction, and then there's a component of the applied force because the guy's pulling at a 30-degree angle. So there's a component of the applied force in the y direction, in positive y direction. And finally, you've got that kinetic frictional force. So put all the forces acting on the point particle, sort of thinking of the box as a point particle, and that's your free body diagram. When setting up Newton's second law, we recognize that this net vector force, so the sum of all the forces acting on the object, is mass times its acceleration. And that splits into really three equations, though we're assuming nothing's happening in the z direction, so we write down two equations. The sum of the forces in the x direction is the mass times acceleration, x direction, and you can see what I've got written here. So the applied force times the cosine of 30 degrees, that's the component in the x direction, in the positive direction, minus the kinetic frictional force is the mass times acceleration in the x direction. And then in the y direction, we've got the normal force in the positive direction minus the gravitational force, mg, and then plus that component of the applied force, so Fa times the sine of 30 degrees. In the y direction, there will be no acceleration. He's not lifting the box off the ground, and it's not sinking into the ground or anything like that. So mass times the acceleration in the y direction will be 0. If you solve for the normal force in this y stuff, then you can substitute that result in where you need it for the frictional force, because the definition of kinetic friction is the coefficient, mu sub k, times the normal force. So we substitute in what we know for the normal force, and you can solve for the acceleration then. So you can see the algebra. I didn't plug in the numbers for you, but there's all the values. So the cosine of 30 is the square root of 2, and you've got the other values that were given. Okay, so that's all for part A. For part B, you're supposed to find the final velocity after this box has moved a distance of 2 meters. And there's another kinematics equation where you've eliminated time. This really is a precursor to work energy theorem, but the final velocity squared is the initial velocity squared plus twice the acceleration times the distance. So just plug in the values we know. It started at rest, so the initial velocity is 0. We figured out what the acceleration was, and we know that the change in position, this distance that it traveled, was 2 meters. So plug the numbers in, take a square root, then you end up seeing that the final velocity is 2 times the square root of that acceleration, which we found in part A. Ta-da! So for part C, you're asked to find out how long it takes. And again, once we knew the acceleration that we got from applying Newton's second law, we're just using those kinematics equations. So, the study of motion without thinking about the cause anymore. So we know the acceleration in the x direction. The equation is that the final position is a half the acceleration in the x direction times the time squared, plus the initial velocity in the x direction times the time, plus the initial position. Now, the initial velocity and the initial position in the x direction is set equal to 0. And we know the final position was 2. And we know what the acceleration was. So again, just a some simple algebra and solve for the time. Showed you the equation, you plug in the numbers that we got from part A, and you're good to go. Okay, Sarah, so this second problem is very similar, but maybe even easier, and the only question I have about the question I have about the question is just about the direction of the applied force. Based on the diagram, we might assume that that's horizontal, so just in like the positive x direction. And I would work the problem that way. So set up the free body diagram. You don't have to deal with frictional forces. Use Newton's second law, and then move forward using kinematics equations from there. If this isn't an adequate explanation or help, then I can provide some more. Just let me know.